So let's move on to the principles and more technical side of regression modeling. So when two variables are correlated and we have enough information to say that there may be a causal relationship between them, then they can be modeled with the use of regression. And in statistics, linear regression is an approach for modeling the relationship between a scalar dependent variable y and one or more explanatory variables denoted x usually. So the case of one explanatory variable is called simple linear regression, and if you have more than one explanatory variables, then this is called multiple linear regression. In linear regression, data are modeled using linear predictor functions, and unknown model parameters are estimated from the data. So such models are called linear models. And linear regression has many practical uses, so most applications fall into one of the two broad categories. So you can either use regression for prediction or forecasting. So that means that you want to fit a predictive model to an observed dataset of y and x values. And after developing such a model, if an additional value of x is given, then you would like to calculate what's the accompanying value of y. So then the fitted model can be used to make prediction. The second family of use is strength of relationship. So given a variable y and a number of variables x1 up to xp that may be related to y, regression analysis can be applied to quantify the strength of relationship between x and all of the explanatory variables. So in that way, we want to assess which of the explanatory variables may have no relationship with y at all, and identify which subsets of the xj contain redundant information about y. So linear regression models are often fitted using least squares approach. And the least squares approach can be used to fit models that are not linear. Thus, although the term least squares and linear model are closely related, they are actually not synonyms. So now if we are given a data set where we have our dependent variable y, and then we have a set of explanatory variables up to p, and each of those has observations from 1 to n. So the regression model assumes that relationship between the dependent variable y and the p vector of regressors is linear. So this relationship is modeled through a disturbance term or error variable epsilon. So an observed random variable that adds noise to the linear relationship between the dependent variable and regressors. And thus the model takes form like this, that our dependent variable becomes a linear combination of predictors multiplied with their model parameters, but plus these error terms, which then accounts for what is missing between the straight line and the actual data. So now if we consider dataset consisting of paired observations, so we would have our dependent variable y, and then we have only one predictor x. So for example, xi could represent height, and yi could represent the weight of the ith person in a random sample of n adult males. So statistical modeling techniques can be used to investigate how the two variables corresponding to the values are related. So in order to do this, it's convenient to think that the data value yi as being observed value of random variable yi, whose distribution depends upon a fixed value of xi. And in here you can also think deeper why we actually model weight using height and not the other way around. Well, a person's height does have influence on the weight, because the taller the person is would normally mean that they are also heavier. Just because if you have equally slim persons, but one is taller than the other, of course the taller one will be heavier than the other one. So then in particular, simple regression model would be written down like this. So it's just a simplified form of the equation we saw before. So we have our predictor with its own parameter. Then we also have the intercept, so that's the constant which may need to be added in the equation, and then we have our error term. So the procedure is referred to as fitting a straight line to the data set. And then the slope parameter beta1 is of particular interest, since it indicates how the expected value of the dependent variable depends upon explanatory variable. And mathematically, fitting a straight line given in here is always the easiest. So therefore, sometimes when we have some data resembling some non-straight but known curve shape, we can transform the data and fit straight line afterwards. So then after the fitting is done, we would transform the fit back to its original shape. And there are some examples in here what kind of transformations we can have. So if the data shape is exponential, we would apply logarithm on it. If the data shape is logarithmic, then we apply exponential or square. And if data shape is parabolic, then we apply square root. And such a transformation should then bring a linear look between our x and y variables.